So this is a great data structure. It solves what we need. It solves substring searching. So this is applications of suffix trees. If I just do a search in the trie for a particular pattern, we get subtree representing all of the occurrences of P in T. So this is great. In order P time, walking down this structure, I can figure out all the occurrences. And so then if I wanted to know how many there were, I could just store subtree sizes, number of leaves below every node. If I wanted to list them, I could just do an in-order traversal. And I'll even get them in order. So in particular, if I wanted to list the first 10 occurrences, I could store the leftmost leaf from every node, teleport down to the first occurrence in constant time, and then I could just have a linked list of all the leaves. So once I find the first one, I can just follow until I find, oh, that's not an occurrence of P. So I can list the first k of them in order k time, once I've done the search of order P time. So this is really good searching, and it's the ideal situation. You can list any information you want about all of the answers in the optimal time, the size of the output. How big is this data structure? Well, there are T suffixes. So K is the size of T. And we look at our trie representations. Our general goal was to get, here capital T was the sum of the lengths. Well, sum of the lengths is not good. That would be quadratic, sum of the lengths of the suffixes. But we also said, or the number of nodes in the trie. And we know the number of leaves in this trie is exactly the size of T. And so because it's a compressed trie, the number of internal nodes is also less than the size of T. So the total number of nodes here is order T. And so if we use any of the reasonable representations, we get order T space. Okay, now there's one issue, which is how long does a search for P cost? And it depends on our representation. It depends how quickly we can traverse a node. If we use hashing, method 3, use hashing, then we get order P time. Okay, but the trouble with hashing is it permutes the children of every node. So in that situation, the leaves will not be ordered in the same way that they're ordered in the string. So if you really want to be able to find the first 5 occurrences of the pattern P, you can't use hashing. You can find some 5 occurrences, but you won't find the first in the usual ordering of the string. So if you really want the first 5, you want them in order, then you should use trays, or this method 6 that we used, 6, 5. If you use trays, then it will be order P times log sigma, because we pay, order P plus log sigma. That was our query time here, P plus log sigma. Okay, a small penalty to pay, but the nice thing is then your answers are represented in order. No permutation, no hashing, no randomization. Okay, so this is the reason suffix trees were invented. They let you do searches fast, but actually they let you do a ton of things fast. And I want to quickly give you an overview of the zillions of things you can do with a suffix tree, and then I want to get to how to build them in linear time, which is some interesting algorithms / data structures. Okay, I already talked about if you want to find the first k occurrences, you can do that in order k time. If you want to find the number of occurrences, you can do that in constant time just by augmenting with subtree sizes. Here's another thing you could do. Suppose you have a very long string. I mean, think of T as an entire document. You know, it could be the Merriam-Webster dictionary, or it could be the web. Okay, so we're imagining T to be a huge data structure, and then we're able to search for substrings within that data structure very fast. So that's cool. Here's an interesting puzzle. What is the longest substring? What is the longest string that appears twice on the web? This is called the longest repeated substring. Could be overlapping, maybe not. Well, you take the web, you throw it in a suffix tree. I'm not sure anyone could actually do that, but small part of the web. Dictionary, this would be no problem, but Wikipedia would be feasible. You take Wikipedia, you throw it in a suffix tree, and if I look, I mean, what I'm interested in is basically a node that has at least two descendant leaves. And if I'm counting the number of leaves at every node, I could just do one pass over this data structure and find what are all the nodes that have at least two descendant leaves. That's all the internal nodes. And then among them, I'd also like to know how deep is it, because the depth corresponds to how long the string is, right? This one is ANA, so this one has I call it a letter depth of 3. This one has a letter depth of 1, this one has a letter depth of 2. So I just want to find the deepest node that has at least two descendant leaves. So in linear time, I could find the longest repeated substring. Or I could find the longest substring that appears 5 times, or whatever. I mean, I just do one pass over this thing, find the deepest node that has my threshold of leaves. So that's kind of a neat thing you can do in linear time on a string. Here's another fun one. Suppose I have this giant string, and I just want to compare two substrings in it. So let's say, so here's my giant string. And I want to, suppose I want to measure how long is a repeated substring. So I say, well, I've got position I, and I've got position j. Let's say I already know that they match for a little bit. I want to know how long do they match? How far can I go to the right and have them still match? How could I do that? Well, I could look at the suffix starting at I. That corresponds to a leaf over here. And I could look at the suffix starting at j. That corresponds to some other leaf. And what is the length of the longest common prefix of those two suffixes in the suffix tree? 3 letters. LCA. Yeah. If I take the LCA of those two leaves, so for example, I don't know, I take these two leaves, the LCA gives me the longest common prefix, then they branch. So longest common prefix of these two suffixes is the letter A. So it's just length 1. And again, if I label every node with the letter depth, I can figure out exactly how long these guys match, even if they overlap. So in constant time, because we already have a constant time LCA query, linear space constant time query, given any two positions ij, I can tell you how long they match for in constant time. Boom. Instantaneously. It's kind of crazy. So you can do tons of these queries instantly. So that's one reason why people care about LCAs. There are other reasons, but mostly LCAs were developed for suffix trees to answer queries like that. Okay, got some more. So why don't I just write LCP of one suffix and another suffix is equivalent to an LCA query. And so we can do that in constant time after preprocessing. Okay, here's another one. Suppose I want to find all occurrences of T I to j. Okay? So I give you a substring, and I want to know where does it occur. The substring is restricted to come from the text. Now, this is a little subtle. I mean, of course, I could solve it in j minus I plus 1 time. I just do the search. But what if I want to do it in constant time? Maybe this is a really big substring, but I still know it appears multiple times. I want to know how many times does it appear. I claim I can do this in constant time. How? Well, this is a level ancestor query. Why is it a level ancestor query? If I look at this suffix starting at I, and then I just want to trim off. I want to stop, or I don't care about the entire suffix. I just want to do that J. It's like saying, well, suppose I'm looking for occurrences of A and A. So I go A and A. So I start at, let's say, the first occurrence of A and A, which is A and a dollar sign. So this is the leaf corresponding to A and A. And then if I want to find all occurrences of A and A, I just need to go up to the ancestor that represents A and A. So this is what I'd call a weighted level ancestor. It's not quite the problem we solved in the last lecture, lecture 15. Because now it's weighted, so it's the level ancestor j minus I of the ti suffix leaf. Okay, so I find this leaf, which I just have an array of all the leaves, give it a suffix, tell me what leaf it is in the suffix tree. And then I want to find the j minus ith ancestor, except the edges don't just have unit length. So here I want to find the third ancestor, except it's really the ancestor in the compressed trie. I want to do the j minus ith ancestor in the suffix, in the trie, but what I have is a compressed tree. And so these edges are labeled with how many characters are on them. And I've got to deal with that. Fortunately, the data structure we gave for a level ancestor, which was constant time query linear space, can be fairly easily adapted to weights. Not quite in constant time, though. It can be solved in log n time. And I think that's optimal. Because even if your thing is a single path with maybe the occasional branch, then finding your ith ancestor here is like solving a predecessor problem, right? Because you say, well, I want to from the ith position up, I want to know what is the previous. I want to round up or round down, so I want to do a predecessor or a successor on this straight line. And so for predecessor, you need log time for the right parameters, and this can be achieved. And the basic idea is you use ladder decomposition just like before, but now a ladder can't be represented by an array because there are lots of absent places in the array. Now instead you use a predecessor, you use a Van Em de Boas to represent a ladder. So that's basically all you do. Van Em de Boas represents a ladder. That's what you do in the top structure. Remember we had indirection, leaf trimming, top was this thing, ladder decomposition, bottom was lookup tables. The other problem is you can't use lookup tables anymore because in one of these tiny trees, you could have a super long path that's non-branching that got compressed, and you can't afford to enumerate all possible situations. Well, that's kind of annoying. So instead of using lookup tables, this was actually an idea from some students in this class last time I taught this material. They said, oh, well, instead of using a lookup table, you can use ladder decomposition. So down here in the compressed tree, we have log n different nodes. If you use ladder decomposition on that thing, but not the hybrid structure, remember we use jump pointers plus ladders. Jump pointers still work here, just you have to round them to a different place. Down here, I'm not going to try to do jump pointers plus ladders. I'll just do ladders. And remember, just ladders gave us a log n query time. But now n is, or this is t, whatever. N is now log t. And so we get log t query time. And that's basically all you have to do. Yeah. So you're always jumping to the top of a ladder. You'll only have to traverse log t ladders. At the very last ladder, you might have to do a predecessor query. That will cost you log t. But overall, it'll be log t time, just by this kind of tweak to our level ancestor data structure. So I thought that was kind of a fun connection. This is the reason, essentially, level ancestors were developed and people use them, because you can do these kinds of things in nearly constant time, even if this substring is huge. So if you imagine, well, maybe I know ahead of time all the queries I might want to do. If I just throw them into the text, just add them in there. Then I've got these substrings that, they're now represented in the suffix tree. And so now any substring I want to query, in log n time, I can find all the occurrences of that substring, even if the substring is huge. So if you kind of know what queries you want, you can pre-process them and solve them even faster than order p time. Cool. Another thing you can do is represent multiple documents, and that's what I was sort of getting at there. If you have multiple documents, say you're storing the entire web or Wikipedia, and like there's multiple pages, you want to separate them. All you need to do is say, okay, I'll take my first string and then put a special $sign after it. Then take my second string, put a special $sign after it. And take my kth string and put a special $sign after it. Just concatenate them with different $signs in between them. Then build a suffix tree on this thing, which I'll call T. So you can use the same suffix tree data structure, but now in some sense you're representing all of these documents and all the ways they interweave. Because there are some shared substrings here that are shared by this and whatever, and those will be represented in the same structure. Or I can do a search, and then I've effectively found all the documents that contain it. One issue, though. Suppose I want to find all the documents containing the word MIT or something. Okay? Maybe all k of them match. Maybe one document matches. Maybe two documents match. Suppose two documents match. The first document mentions MIT a billion times. The second document represents it, has MIT in it once. Then suffix trees are kind of annoying because they will find that billion and one matches as a subtree. But if I just want to know the answer, oh, these two documents match, I'd like to do that in order 2 time, not order billion time. To use technical terms. Okay? And that is called the document retrieval problem, or document retrieval data structure. This is a problem considered by Muthukrishnan in 2002. Document retrieval you can do in order p plus log, p plus number of documents matching. So if I want to list all the documents that match, I could do it in order the number of documents that match, not the order of a number of occurrences of the string. So I still got to do the p search in the beginning, and then this is better. And the fun thing is the solution to this data structure uses RMQ, range minimum queries from last lecture. So let me tell you how it works. It's actually very simple. And then I think we'll move on to how to build a suffix tree. So document retrieval. Here's what we're going to do. Okay, remember these different $I represent different documents. In some sense, I want to remember which suffixes came from the same document. Okay, so at every I want to store the number of the previous $I. Okay, let's suppose the suffixes, when they get to one of the $, I can just stop. I don't have to store the rest. I'm going to throw away. Whenever I hit a $, I will stop the suffix tree. So that way the $s really are leaves. All of them now become leaves. So I don't really care about a suffix that goes all the way through here. I just want the suffix to the $. So those represent the individual documents. So $I's are leaves. And I want each of them just to store a pointer, basically, to the previous one of the same type, the same $I. Came from the same document. Okay, so what? So now, here's the idea. If I did a search, I got down to a node, and now there's this big subtree here. And this subtree has a bunch of leaves in it. Those represent all the occurrences of pattern P. So this is P. And let's suppose that those leaves are numbered. I'm numbering the leaves from 1 to n, I guess. Then in here, the leaves will be an interval. Interval L comma n. And the trouble is a lot of these have the same label $I. And I just want to find the unique ones. How do I do that? What we do is find the first occurrence of $I for each I. If I could just find the first occurrence of $I for each I, then I only have to pay order number of distinct documents. I won't have to pay for every match within the document. Now, one way to define the first $I is that's a $i whose stored value, we said we store the leaf number of the previous $i, whose stored value is less than L. If the previous guy, so we find some position here, if the previous guy is less than L, that means it was the first of that type. Okay, so that's just, if we store this, that's the definition of being first. So I want to find, in this interval, I want to find $i's that have very small stored values. How would I find the very best one? Range minimum query. So we do a range minimum query on L comma N. If there's any firsts in there, this will find it. Find, let's say, position M with the smallest possible stored value. Okay, if the stored number is less than L, then output that answer. And then recurse on the remaining intervals. So there's going to be from L to M minus 1 and M plus 1 to N. So we find the best candidate, the minimum. That's minimum stored value. If anything's going to be less than L, that would be it. If it is less than L, we output it. Then we recurse over here, and we recurse over here. At some point, this will stop finding things. We're going to do another RMQ over here. Might not find anything. Then we just stop that recursion. Okay, but the number of recursions we have to do is going to be equal to the number of documents that match, maybe plus 1. Okay, so we achieve this bound using RMQ, because RMQ we can do in constant time with appropriate preprocessing. Now, the RMQ is over an array. It's over this array of stored values indexed by leaves. And this idea of taking the leaves and writing them down in order is actually something we need. It's called a suffix array. We're going to use this alternate representation of suffix trees in order to compute them. Suffix arrays, in some sense, are easier to think about. The idea with the suffix array is to write down all the suffixes, sort them. This is conceptual. Imagine you take all these suffixes. Their total size is quadratic in T, so you'd never actually want to do this. But just imagine writing them down, sorting them lexically using our string sorting algorithm, say. And then we can't represent them explicitly because it would be too big. Just write down their index. So just store the indices. Okay, let's do this for banana. Oops, banana is over here. Make my life a little harder. Banana. So, actually, they're already here in sorted order. If $sign is, I'm supposing sorts first. First suffix is $, then $, then $ANA $, then ANA $, then banana, then NA $, then NA $. So I'll just write that down over here. $, $, ANA $, $, then banana, then NA $, then NA $. If you look at these, they are indeed in sorted order. $, A's, B's, N's, and everything is sorted here lexically. Okay, now I can't store this because it's quadratic size. Instead, I just write down the numbers that are down there. This was the sixth suffix. It was starting at position 6. Then 5, then 3, then 1, then 0. That's everything. Then 4, then 2. This thing is the suffix array. It also has linear size. It's just a permutation on the suffix labels, suffix indices. What else do I want to tell you about it? There's some other information that's helpful to write down about the suffix array. It's called longest common prefix information, LCP. The idea is to look at adjacent elements in the suffix array. In some sense, this represents the same information, right? Our whole goal is to sort the suffixes. If we could do this, then, as we'll see, we can also build this. And this is sort of what we really want. The suffix array by itself is pretty good if you add in LCP information. LCP is what is the longest common prefix of these two suffixes. In this case, 0. In this case, 1 letter. In this case, 3 letters match. So here, the value is 3. And next one, 0 letters match. Next one, 0 letters match. Next one, 2 letters match, NA. Okay, so this is another array you could store here. 0, 1, 3, 0, 0, 2.
Longest common prefix?
Longest common prefix of the suffixes. Because each of these is a suffix, but here we're interested in how long they match for. I claim if you have this suffix array and this LCP information, you can build this structure. Anyone want to tell me how to build this using this? So 1 word or 2 word answer that we saw, I think, last class. But we saw a lot of things last class, so it's maybe not obvious. Magic words are Cartesian tree. Cartesian tree was how we converted RMQ into LCA, I think, yeah? Which was you take the minimum value in the array, make that the root, and then recurse on the 2 sides. In this situation, so a Cartesian tree of the LCP array basically gives you this transformation. The minimum values here are the zeros. Now, before we just broke ties, we picked an arbitrary 0, put it at the root. Now I want to take all the zeros, put them at the root. If I do that, I get 3 zeros at the root, and then I have everything in between. So there's nothing left of the first 0. Then next one, there's these guys, and if the min's going to be 1 and then 3. So here I'm going to get a 1 when I recurse, and then a 3. Okay. Then there's nothing in between these zeros. Then after the last 0, there's a 2. So this would be the Cartesian tree, a slightly different version where we don't break ties. We take all the mins simultaneously, put them at the root. Now, does that look like this thing? Yeah. Everything except the leaves. All we're missing are the leaves. The leaves are represented by these values. So just visit them in order here. Do an in-order traversal of the missing pointers here. We're going to get a 6, and then a 5, and then a 3, and then a 1, and then a 0, and then a 4, and then a 2. Now the meaning of these values is slightly different. Maybe I should circle them in red. These leaves are just like these leaves. They're exactly the labels we wrote down in the same order. These numbers are slightly different. What they represent are letter depths. The letter depth of this node is 0. Letter depth of this node is 1. Letter depth of this node is 3. That's what I wrote here. 1, 3, 2. This one says 2. These LCPs are exactly the letter depth. That's how far down the tree you are. Once you have this structure and the letter depths, you can very easily put in these labels. I won't say how to do that. But in linear time, if I could build the suffix array plus the LCPs, I could build suffix tree. Okay, so our real goal is to build this information, these 2 arrays. If we could do it in linear time, we'd get a suffix tree in linear time. So that is what remains to be done. So we're going to do not quite linear time. If you want a nicely sorted suffix tree where all the children are labeled here. So in particular, if I just had a single node, I have to be able to sort the letters in the alphabet. Okay? So however long that takes, maybe it's a small alphabet, you can do linear time sorting by radix sort or whatever. However long that takes, we do it once, then the rest will be order t time. Here's how we do it. First step, sort the alphabet. Okay, this will turn out to be more interesting than you might think. I'll come back to it. Second step, replace each letter by its index in the sorted order. This sounds boring, but it will be useful for later. Third step, the big idea. This is an algorithm by Karkanian and Saunders from 2003. The problem was first solved in this running time by Martin Farch Colton, our good friend. But then it got simplified. So I'll tell you a little bit about that in a moment. Okay, and there's going to be a lot of writing here. Equals 0, 1. Okay, the idea here is we're going to take the 3i letter, 3i plus first, 3i plus second letter, concatenate them into a single triple letter. Think of it as a single letter. And then just do that for all I. So it's like I take these guys, make them one letter, these guys, make them one letter. Now I could start at 0, or I could start at 1, or I could start at 2. Do them all. So this is going to be 3i plus 1, 3i plus 2, 3i plus 3. And this one's going to be 3i plus 2, 3i plus 3, 3i plus 4. Okay, we'll see why. We're going to do this to recurse. But the point is, if I want to represent all the suffixes of t, suffix could start at a position 0 mod 3, or a position 1 mod 3, or a position 2 mod 3. So if I could sort all the suffixes of these guys, I would effectively sort all the suffixes of the original t. This tripling up doesn't really change things, up to like a plus 1 or 2. Okay. Now what? Next, I believe, is recursion. Yeah. I'm going to take T0 and T1 and concatenate them. This thing has size 2/3 n. It has number of characters 2/3 n, because each of them has a third of the number of characters. Of course, all the information is still there, which is kind of weird. But if we treat this as a single character, each of them has a third n. We can't afford to recurse on all 3. We can only afford to recurse on 2 out of the 3, because then we're going to get a recurrence of the form t of n is t of 2/3 n plus order n. And this is geometric, so that's order n. That's how we're going to get linear time after the first sort. If this was 3/3 n, then this would be n log n. We don't want to do that. Okay, so that's what I can afford. Now I've got to deal with it. What this tells me is the sorted order of all the suffixes of T0 and T1, all the suffixes starting at positions that are 0 or 1 mod 3. So next thing we'd like to do is sort the suffixes of T2. And we can do that, I claim, by radix sort. How do we do that? Well, if you look at a suffix T2i, this is the same thing as t from 3i plus 2 onwards, okay, which we can think of as that first character, comma, the next character onwards. Okay, which we can, sorry, that's an angle bracket. And this thing is basically T0 of I plus 1 onwards. Okay, so if I strip off the first letter, then I get a suffix that I know about. I know the sorted order of all the T0 suffixes. So this is really just you can think of this as a 2-character value. There's a single character from sigma here, and then which we've already reduced down to, this is an integer between 0 and sigma minus 1. This thing, you can do the same thing with these recursive values. So you've just got 2 values, small. You can radix sort them in linear time. And then we will have sorted the T2 suffixes because we already knew the order of these guys. OK, one more thing, which we have to merge suffixes of T0 and T1 with the suffixes of T2. And this is where we use the fact that there are 3 of these things and not 2 of them. This is a weird case where 3-way divide and conquer works. 2-way divide and conquer is what Farage-Colton did originally. It's much more complicated because of this merge step. Merge gets painful. I claim this merging is easy because if I need to, all I need is merging is linear time provided your comparison is constant time. So if I need to compare a T0 suffix with a T2 suffix, if I want to do that comparison, I strip off the first letter from this one, it turns into a T1 suffix. It's the first character plus a T1 suffix. I strip off the first character of this one, it turns into the first character and then a T0 suffix. And these things I know how to compare because I already sorted T0, T1. If I need to compare a T1 suffix with a T2 suffix, how do I do it? I strip off the first 2 letters of this one, I get a T0 suffix. I strip off the first 2 letters of this one, I get a T1 suffix. I can't strip off 1 letter because this would turn into a T2, and I don't know how to compare a T2 to other things. That's the whole point. Well, I guess it's a T2 versus a T0 if I did that, which is this case. But here, if I strip off 2 letters, I get something I know how to compare. This technique does not work if you only have 2 things. It only works if you have 3 things, because there's sort of these situations. So constant time, by comparing these little tuples, the first character or 2 plus the remaining suffix, I can do the comparator in merge. And then if I can do that, everything is linear time. The only interesting thing is how do I sort the alphabet when I recurse? And for that, you use radix sort. So the first time you pay sort of sigma. We don't know how long that takes. Depends on your alphabet. But every following recursion, it's a radix sort because you have a triple of values, each of which is small. And so you can do it in linear time because there's only three digits to the thing you're sorting. So overall, this is a recursive algorithm. Gives you linear time because you're making one recursive call of 2/3 the size. Pretty clever and simple. And that's suffix trees and how you build them. You get suffix arrays. You can do the same thing and get LCP information at the same time. It's written in the notes. Then you get suffix trees, and then you're done.